Right, hello everybody, welcome back to another video. In this video, we're going to be looking at a question from an HL Chemistry Paper 1 from the November 2020 batch. So this question asks, which molecule is the most polar? And they've given us these four options over here. Now, when considering or when determining if a molecule is polar or not, you have to first look at two things. You have to look at the electronegativity difference between two atoms which are covalently bonded. And in this case, all of these atoms are covalently bonded to a central atom. And the central atom in this case is carbon. So carbon will be the central atom. And if you have trouble determining what the central atom in a molecule is, just remember that the least electronegative atom in the molecule will be the central atom. So in this case, carbon is a central atom because it is the least electronegative out of all of them, with an exception for hydrogen over here. And the reason why hydrogen cannot be the central atom is because it only has a capacity to accept two electrons, and that doesn't make it an ideal central atom because it can't be covalently bonded to more than one other element. So carbon is a central atom. We're just going to draw carbon over here. Now, what we have to consider is that the difference between the electronegativities of the two atoms bonded covalently to each other. So for the sake of this example, I'm going to take CF4. So carbon in this molecule is covalently bonded to four other fluorines. So in order to calculate the electronegativity difference, you have to, of course, find the electronegativity of atom number 1 and atom number 2, and you have to subtract the electronegativity of the atom, which is higher, minus the electronegativity of the atom, which is lower. So in this case, fluorine has an electronegativity of 4.0, and it's actually the most electronegative element in the periodic table. And carbon has an electronegativity of 2.6, I believe. Now, of course, this is a paper one, and you're not going to have access to the full data booklet. So really all you need to know is that the most electronegative negative atom is fluorine, and oxygen comes in with a close second. Chlorine is also very electronegative, and so is nitrogen and boron. Nitrogen and boron have the same electronegativity. So you really only need to remember these 4 or 5 elements. Just remember that fluorine is the most electronegative, and oxygen is also quite electronegative. Now, let's look at, so the difference of electronegativities is actually what we use to determine if a covalent bond between two elements is polar or not. And in this case, this is a polar bond because of the electronegativity difference is quite high. And that would mean that all of these bonds are also polar. Now, despite these bonds, all of these bonds being polar, the overall molecule, the polarity of the overall molecule, not just the individual bonds, but the overall molecule also depends on one other factor, and that is the molecular geometry. Molecular G. I'm just going to call it the molecular G. It's called the molecular geometry. Now, in this case, in order for a molecule to be polar, it must have one positive end and one negative end. Now, in the instance of HCl, this is a molecule, chlorine is slightly negative and hydrogen has a slightly positive charge because of the electronegativity difference. This chlorine has a tendency to pull the electrons towards itself. And it's the exact same case in this molecule above. All the fluorines have a slight negative charge, and the carbon has a slight positive charge. That means that the dipole moment is towards the fluorines. So in a dipole moment, this represents the positive end, and this represents the negative end. So that's what a dipole moment is. The dipole moment is moving towards the negative end of the molecule. So they all have a dipole moment towards the fluorine. Now, despite there being 4 different dipole moments, you would assume that this is a polar molecule, but this is actually not the case. All these dipoles cancel out because of the symmetry of this molecule. The molecular geometry of CF4 is tetrahedral. And you can think of it like a tug of war. All these fluorines are tugging the electrons away from carbon in the exact same strength. So actually, the electrons, you could think of carbon or the electrons not really going anywhere because of these dipoles. They're all applying the exact same force. And that the resultant change is zero. So meaning the resultant charge is zero, meaning that the electrons are actually going to no single fluorine. That means there is not a bias or a attraction of electrons that is stronger than the other atoms. So all of them have an equal attraction for the electrons, and that means that the dipoles cancel out, making this molecule non-polar because the electrons are being pulled equally in all four different directions, and that cancels out. You could think of it like a tug of war. So supposing you have a bar of gold, solid gold, right? And there are two teams that want this gold. So there is team number one, which is pulling the bar of gold from one side, and there is team number two, which is pulling the bar of gold from another side. And both these teams are applying the same force. They're applying 10 force, for example. Both of them are applying 10 force. This would basically mean that the bar of gold ends up going nowhere because these forces cancel out, right? It continues to remain in the spot that it originally was. And it is somewhat similar with determining the polarity of a molecule. It's probably a very poor analogy, but I hope you kind of get the idea of what I'm talking about and about the dipole moments canceling out. So this is what makes the molecule non-polar. Now, since CF4 is non-polar, we can actually take it out. It's out of the option. And CCl4 is exactly the same thing. It's the same as CF4. There are the same four elements. The bonds of each bond in this molecule is polar. They're all polar, but the dipole moments all cancel out, right? The dipole moments are all towards chlorine. The molecular geometry is tetrahedral and they all cancel out, making this molecule non-polar as well. So this is also out of the question. So now we're left with the last two options. We're left with CHF3 and then we're left with CClF3. And out of these, the correct answer is CHF3 and not CClF3. Now, you may ask, why is that the case? All even CClF3 it won't necessarily have a dipole or an equal dipole moment, or the dipole moments won't cancel out in this case because chlorine is less electronegative than fluorine. So the dipole moments won't cancel out, even though there is a dipole moment towards chlorine here. The fluorines still have a dipole moments towards them and they are more electronegative. So this shouldn't cancel out, right? But they have asked which molecule is the most polar, and the electronegativity of chlorine and fluorine is actually quite similar. Chlorine is 3.2 and fluorine is 4. I mean, it's nearly the same, right? It's the difference isn't so wide apart. Unlike in this case, where there is a hydrogen instead of chlorine, and hydrogen it's practically it practically has the same electronegativity as carbon. There isn't even a difference. It's barely a difference. It's only a difference of 0.2. Hydrogen has a electronegative 2.2, and carbon has an electronegativity of 2.6. Sorry, there's 0.4 difference. It's very little, right? So that's why these fluorines are then able to pull the electron towards themselves, and dipole moments don't cancel out because there's a strong tug over here. You can kind of imagine, we can take the gold bar analogy again. There's a gold bar. There are two teams that decide to pull it, but this time one team is applying 100 force and the other team is applying only 10. And that means that the gold bar will go towards the team which is applying more force. And it's quite literally the same case over here. These fluorines are applying or they have a higher electronegativity, and this results in the electrons being pulled to this side, making it negative, this side of the molecule, and this ends up making the molecule polar. So that this is the most polar molecule that there is. That's why A is the correct answer. I know this is quite a tricky issue to understand, or a tricky concept to understand. I'm not going to lie, even I have some difficulty explaining it in the right words. But I hope you've understood what I'm trying to say. I hope you've understood my rather weird gold bar analogy, and hopefully this can help you in your exam to answer such questions. Thank you so much for watching it. If you have any questions regarding this concept or any other concepts, please let me know down below in the comments, message me on my social media, or send me an email. I'll be more than happy to help you. Thank you so much for watching, and I will see you in the next video with another question.